This lesson is on vectors and applications. We assume that you've had some experience with vectors in this lesson, and so if that is not true in your case, you may want to go to the library and check out another video on vectors to get some background information. We're simply going to do a quick review of a couple of vector concepts for this particular lesson, and then we will move right on into the trig application type problems using vectors. The first matter of review is that we want to consider that vectors have both magnitude and direction. Geometrically, they are represented by directed line segments. You might recall that the magnitude of a vector is depicting its size, how long it might be. And generally magnitude is represented in terms like in pounds or miles per hour or some other quantity like that that we consider having magnitude or size. The direction is sometimes measured from horizontal. It is sometimes given in navigation circles through bearing, and we will be reviewing some of those concepts as we do the problems. The second concept in this vector review is to recall that vectors can be added geometrically using the parallelogram rule. Now, if you have not had experience with the parallelogram rule, I'm going to review that with you a little bit here. But basically it involves drawing a parallelogram and then using that to solve our problems. The parallelogram rule for vector addition states that we should place vectors u and v with initial points coinciding. Complete a parallelogram with u and v as adjacent sides. The diagonal r with the same initial point as u and v is the sum or resultant of u and v. Let me demonstrate that here with just this example. If we have the vector u with its initial point and going in this direction, and then we have another vector v, notice I'm placing them with their initial points coinciding, then we will use these two vectors to complete a parallelogram. The resultant, again, has this same initial point and goes to the opposite corner. This will be the resultant vector r. Having looked at this parallelogram rule, we're now going to look at a trig problem where we're going to use the parallelogram rule to help us draw our picture, and then we're going to be appealing back to some of the things that we've learned in trigonometry to help us solve this problem. Two forces, 12 newtons and 25 newtons, act on an object. The angle between the forces is 103 degrees. Find the magnitude of the resultant force. Now here we simply are given two vectors with an angle between those. We're not given any specific direction, so we can just choose an initial point that we'll use as the common initial point. Let's just draw one vector sort of horizontally out this direction. We'll call this the 12 Newton vector. And then since we know our angle is 103 degrees, let's be sure that we go more than 90 degrees over. And we will draw a second vector coming out here that will represent our 25 Newton force. Now we will use these to complete our parallelogram as we talked about before. Then from this same initial point we're going to come across to that opposite corner with our resultant vector r. We want to find the magnitude or the length of this resultant force here. Now, in order to solve this problem, now that we have our picture, we're going to recall some properties of parallelograms. First of all, recall that opposite sides of a parallelogram not only are parallel, but also have the same length. So this side of my parallelogram also has a length of 25. Now, I'm going to go ahead and shade that in darker. And what I want you to concentrate on is the triangle that we have formed here. We know two of the sides of that triangle. Let's see what else we can figure out about this triangle. Recall the angle between the original two forces is 103 degrees. From this 12 Newton force all the way over to the 25 Newton force, this whole angle right here is 103 degrees. In a parallelogram, you might recall that adjacent angles of a parallelogram are supplementary. Supplementary means that they add together to equal 180 degrees. Therefore, 180 degrees minus the 103 degrees that we have here leaves us 77 degrees for this angle right here in our triangle. Now again, we want to find this side. We know two sides and the included angle. You might recall from previous lessons that we can use the law of cosines to solve problems like this. I'm going to state first of all one form of the rule of the law of cosines. C squared equals a squared plus b squared minus 2 times a times b times the cosine of angle C. You might recall in the law of cosines that generally the side you do not know, if there is a missing side, we put here. And the angle is always the angle opposite this side that's over here. The other two sides we square and add together, and then in this part of the problem it's twice the product of these same two sides that are here. In our problem, since we do not know this side here, we're going to say r squared equals, we know the side 12, so 12 squared, plus we also know 25 squared, minus 2 times 12 times 25 times the cosine of the angle between this 12 and 25, which is 77 degrees. Now, let's go to our calculator, and first of all, I'm just going to get an approximate value for r squared. Now, as you go to your calculator, recall we're working with degrees here, so be sure your calculator is set for degrees. So let's see, we want 12 squared plus 25 squared minus 2 times 12 times 25 times the cosine of 77 degrees. For r squared, I'm just going to write down part of this. I have 634.029. Okay? Now, of course, we don't want r squared. We want the magnitude or the length of r, so we need to take the square root here. So, taking the square root, my calculator, of course, is showing quite a few decimal places. So, let's recall our general rule. If our angle is given in degrees, we generally keep two significant digits. So, I'm going to round this off, and r will be approximately 25 newtons for its magnitude. This next problem involves what we call vertical and horizontal components of a vector. Notice we have vector v has a magnitude of 15 and is inclined from horizontal at an angle of 38 degrees 12 minutes. We are to find the magnitude of the vertical and horizontal components of v. Well, again, let's get a picture. Let's choose an initial point here, and since our angle is given from horizontal, I'm just going to draw a line out to the right here to be my horizontal direction, and then I'm going to incline up 38 degrees 12 minutes. Let me mark that angle, 38 degrees 12 minutes. Let me extend this long enough that my picture can go across that writing. Okay? Of course, we're just getting a sort of a representation. Our picture doesn't have to be perfect. Okay, so this vector that's inclined from the horizontal, 38 degrees 12 minutes, has a magnitude of 15. So the length of this vector going up here is 15. Now, as you might guess, vertical and horizontal components, here's horizontal and here's vertical. Here's what we do. From the terminal point of my vector, I'm going to drop a perpendicular or vertical line down to this horizontal line. I'm going to call this V, and I'm going to call this part H. My horizontal component will be the length, the horizontal length, if you will, that you have to go over to be under the terminal point of your vector. And this distance here is the vertical component. That's how far above horizontal you have to go to be, again, at the terminal point of that vector. Okay, so to find this vertical component, we're going to look at this triangle and notice that it's a right triangle. If you have a right triangle, then your simple trig functions using a right triangle can be used. Recall that the sine of an angle in a right triangle is the opposite divided by the hypotenuse. So let's write that down. We know that the sine of 38 degrees 12 minutes can be found by taking the side opposite that, which is V, and dividing by the hypotenuse 15. Now to solve this for V, we're going to multiply both sides by 15, and this 15 over here will cancel out. So our vertical component can be found by multiplying 15 times the sine of 38 degrees 12 minutes. Now recall that you need to convert from degrees and minutes into decimal degrees in order to find on your calculator the sine of that. Many of you have calculators will do that will do that conversion automatically. Mine will, so I'm simply going to key this in, 15 times the sine, and now I'll use my conversion key, 38 degrees 12 minutes, which turns out to be 38.2 degrees if you're doing that conversion separately. And so for this I have again several decimal places, and so let's remember that when we are given degrees and minutes like this, then we can go to 4 significant digits. So using 4 significant digits, I have 9.276 for my vertical component. For the horizontal component, again, we're going to use a trig function. The cosine of an angle is the adjacent side divided by the hypotenuse. So the cosine of 38 degrees 12 minutes will be the adjacent side, which we've called h, divided by 15, the hypotenuse. Again, we'll multiply both sides by 15. And then again, to find this horizontal component, we can simply multiply. So we need 15 times the cosine of 38 degrees 12 minutes. And again, since we have minutes here, we're going to use 4 significant digits, which will give me 11.79 for the horizontal component. We're going to look at a definition of what we mean by the equilibrant of a vector in order to use that to work our next problem. The equilibrant of a vector V is the vector that will counterbalance it. Thus the equilibrant of V is negative V, or the opposite of V. If you're going to counterbalance, basically that means to cancel out a vector. So what you need is a force of the same magnitude but acting in the opposite direction, and that of course is what this negative V or opposite V is explaining here. Same magnitude but simply opposite directions. Find the magnitude and direction of the force necessary to counteract the effect of a force of 60 pounds and a force of 40 pounds that act on a point at an angle of 60 degrees with each other. In other words, we want the equilibrant of the resultant of these vectors. Okay, let's choose an initial point. And again, we know that these two forces of 60 pounds and 40 pounds have an angle between them of 60 degrees. So let's just draw a vector out this direction, and we'll call this one the 60-pound force. We'll go about 60 degrees, and we'll have another vector that is a 40-pound force. This angle again is 60 degrees. Now what we're going to do is to complete our parallelogram. The resultant, of course, is the same initial point cutting across to this opposite corner. Let's call that R. And if we want to find the equilibrant of the resultant, we want to find the opposite of R. Now I'm going to talk about how we're going to explain the opposite of r here in a second. The first thing we need to do is to find the magnitude of our r. So as we've done in previous problems, the side opposite has the same length. So this side over here is 40 degrees. Let me close that off. If this angle is 60 and these two angles are supplementary, then this angle is going to be 120 degrees. And we can use the law of cosines again to help us find the magnitude of r. So r squared is going to equal 60 squared plus 40 squared minus 2 times 60 times 40 times the cosine of the included angle here, 120 degrees. Okay? Now let's go ahead and go to our calculator and let's get a value for r squared first of all. Okay, 60 squared plus 40 squared minus 2 times 60 times 40 times the cosine of 120 degrees. So for r squared, I have 7,600. Now, let's get r. We'll take the square root of 7,600. Now again, I'm getting decimal places, but we're given degrees here, so we'll keep two significant digits. So r is approximately 87 pounds. Let me label that, okay? Now, we know that the equilibrant also has to be 87 pounds, but it's going to act in an opposite direction. So the equilibrant, let me call it E here for equilibrant. R is going this direction. It has a magnitude of 87. The equilibrant, or the counteracting force, counterbalancing force, is going to also be 87 pounds, but it's going to be acting in an opposite direction from R. So we know that E is also approximately 87 pounds, but we need to describe some direction for E. Now, because we were not given specific angles from horizontal or anything like that for our original forces, here's what we're going to do to give a direction to our equilibrant. We can either find this angle between the 40-degree force and the equilibrant, or we can find this angle between the 60-degree force and the equilibrant. Either of those would give us some indication of the direction. I think I'm going to choose to find this angle right here, which I'm going to call angle theta. Okay? Now, let's do a little bit of thinking here. Since vector r and vector e are opposites, going exactly opposite directions, we know that they form a straight line, 180 degrees, if you will. This angle between the resultant and down to this 60-pound force, I'm going to call alpha. So we know that alpha plus theta is 180 degrees. If we can find angle alpha, then we can solve for angle theta, can't we? Well, let's go back and recognize that angle alpha is here in this triangle that we've been using. We now know the length of this third side, so we know all three sides of our triangle, and we also know this 120 degrees. Let's use the law of sines to help us find angle alpha. So let's see, I'm going to put the sine of angle alpha over the side opposite that, which is 40, and I will set that equal to the sine of the 120 degree angle that we know, and the side opposite that is r, or 87. So if we cross multiply here, we have 87 times the sine of alpha is 40 times the sine of 120 degrees, and then of course we can divide both sides by 87, and we'll solve this now to find the sine of angle alpha, and then we'll be able to do an inverse sine and find that degree measure. So let's get this value here. 40 times the sine of 120 degrees. We're going to divide that by 87. So this is approximately 0.39817. I'm just going to put that many decimal places down. Okay? Now, I don't want the sine of angle alpha. I want the sine. So I'm just going to use my calculator and do an inverse sine now to find the angle. So using that, alpha is approximately 23 degrees. I'll round off. Okay, so theta is going to be 180 degrees minus 23 degrees. Okay, so 180 minus 23 gives me about 157 degrees. So what we're going to say, E is 87 pounds, and it is at 157 degrees from the 60-pound force. Okay? And that will give us some measure of the direction of this equilibrant. Find the force required to prevent a 500-pound object from sliding down a 40-degree incline disregarding friction. Now you'll find that most of what we call these incline plane problems are set up very similarly. But let's start by looking at this situation. Again, I'm going to choose a point, and let's go horizontal. And then if we have a 40-degree incline, I'm going to incline up here 40 degrees. I'm going to make this picture rather large because I want to be sure that you can see all the things that are necessary here. Okay, so somewhere on this inclined plane I have an object that weighs 500 pounds. Okay, and what we want to know is what force do we have to exert up to keep it from sliding down this way. Now, here's a couple of concepts that you need to work these inclined plane problems. When you have an object sitting here, there are a couple of forces that work. One is acting vertically downward. That's the pull of gravity. Okay? So this force coming down is the pull of gravity, which is going to be the same thing as the weight of our object. So this vector coming down has a magnitude of 500. Now, in addition to that force, there is a force that acts perpendicular to the plane that holds that object there against the plane. So let's come down something like this. Notice this is 90-degree angle right here. Okay? Now, if I look at these two forces, okay, and I think about this being my plane, I'm going to come down here parallel to this coming down here. And if you look at your parallelogram, the force here, I'm going to call it F, will be the same as the force of this thing sliding down this direction. So if I can find F, then I will need the equilibrant or the opposite of F to pull up to keep that thing from sliding down. Now, if this is parallel to my plane and this is perpendicular to my plane here, then this is also perpendicular here. So I've got a right triangle here to work with. Now, here's something else to think about. Since this was the pull of gravity coming straight down, this is a vertical and this is a horizontal. So this is 90 degrees right here. In this right triangle, if this is 40 degrees and this is 90, then this has to be 50 degrees right here. But since this incline right here and this force coming this way are perpendicular, if this is 50, then this angle is 40. And you'll find that that's always true. Now, you may not can read that 40. The angle here between the force acting directly downward and perpendicular to the inclined plane is always the same as this angle of inclination. What I want us to concentrate now on is this right triangle that we have formed here. I know the hypotenuse of this right triangle is 500, and I know this angle here is 40 degrees. The sine of an angle in a right triangle, so the sine of this 40-degree angle is the opposite side, which is F, divided by the hypotenuse, which is 500. So, as we've seen before, if I multiply both sides of this equation by 500 to cancel this out, I will have F. So, going to my calculator, 500 times the sine of 40 degrees, and again, since we're working with degrees here, we're going to keep two significant digits. So I'm going to round this off to 320. Okay, for two significant digits. So my force is about 320 pounds that I'm going to need to exert. And of course the force is going to need to go up the incline. So the force that I need is 320 pounds up the incline to counterbalance the force coming down the incline to keep that object from sliding. The last two problems that I have on this video have to do with using bearing to help us to find the direction of vectors. You're going to find that these problems are very important to get an accurate sketch in order to see how to solve the problem that we need. When you're given bearing and you're simply given one angle, if it says on a bearing of 35 degrees, you have to remember that that means you start from a north direction and you go clockwise. So we'll be using that concept as we work these next two problems. A boat travels 25 miles per hour in still water. The boat is traveling on a bearing of 130 degrees. The current in the river has a speed of 7 miles per hour and is coming from the west. Find the resulting speed of the boat and its resulting direction of travel. You know, of course, that as boats are in the water, the current of the water can move those boats off of their initial bearing, and it can also affect the speed of the boat if the current is acting against the boat. The same thing is true of airplanes as they fly in the air if you have a wind current, which you'll see in the second example. So we're going to see how we can draw examples of these forces and get us a resulting triangle to work with. Okay, well, let's see if we can get this problem. Our boat is traveling on a bearing of 130 degrees. So as I said, let's think about north. Okay, so let's pick a point and let's think, okay, here's north. We're going to go clockwise. Okay, so going around 130 degrees, that's more than 90 but less than 180, our boat is starting out traveling in this direction. And since the boat is traveling at 25 miles per hour, I'm going to label this vector with a magnitude of 25. Our boat is starting out heading this way. Now, the current in the river has a speed of 7 miles an hour, so we're going to use a vector of magnitude 7 to represent that. Notice it says it's coming from the west. Okay, well, this direction is west. If it's coming from the west, it's going from west to east. So what I'm going to do is from this point right here, we're going to go to the direction of the east. So we're coming from the west, headed toward the east at 7 miles per hour. So this current is going to cause our boat to kind of go off course and head this direction, isn't it? Okay, we're going to use our parallelogram rule here. We're going to complete our parallelogram. And our resultant will be from that same initial point across over here. So let's call this R. We want to find the resulting speed of the boat. That would be the magnitude of R, and the resulting direction of travel. Okay, well, let's start with the magnitude. Let's see what we can do about learning about some angles here. Of course, we know this opposite side is 25. And let's see. What can I know about any of these angles? Well, let's see. If this is 130 degrees, but I know from here to here is 90 degrees, don't I? Well, 130 minus 90 gives me what, 40 degrees? So the angle from here to here is 40, okay? adjacent angles are supplementary. So this angle right here is going to have to be 140 degrees, isn't it? Okay, you see how we arrived at that? 140 degrees plus the 40 degrees here makes 180, and we got the 40 because we know this is 90, so 90 from the 130. Okay, so now we can concentrate on this triangle right here. Okay, so the side opposite the 140 is r, so we know r squared is going to equal 7 squared plus 25 squared minus 2 times 7 times 25 times the cosine of that 140 degree angle. So as we've done before, let's get a value for r squared first, and then we'll go from there. So we have 7 squared plus 25 squared minus 2 times 7 times 25 times the cosine of 140 degrees. Let me write down what I've got, 942.116 roughly. Now we'll square root that to get r. And again, we're given degrees here, so let's keep two significant digits as we do this. So r, rounding to two significant digits, is about 31. So we're going to say that the speed of the boat is about 31 miles per hour, the resulting speed. Now, we need to give the direction, and since all of these directions have been given in terms of bearing, we want to do the same. Now, if I can find this angle right here, I can add 90 degrees to that. Let's call this angle alpha. The bearing is going to equal 90 degrees plus alpha, isn't it? Okay, well, let's look at alpha. Alpha is opposite this 25, so the sine of alpha divided by 25. We now know r is 31, and that is opposite that 140 degrees. So the sine of 140 degrees over 31. Okay, well, let's do some cross multiplying here and see if we can solve for alpha. 31 times the sine of alpha equals 25 times the sine of 140 degrees. We're going to divide both sides by 31 to get the sine of alpha. So let's go ahead and calculate that. We have 25 times the sine of 140. We're dividing that by 31. So for the sine of alpha, I have about 5.5184. Then we're going to do an inverse sine. And since we're using degrees here, let's round that off. Alpha is going to be approximately 31 degrees. Okay? So let's come back up here. Our bearing then is 90 degrees plus 31 degrees. Was that 121 degrees? So the resulting bearing of our boat is about 121 degrees, and our resulting speed is 31 miles per hour. Sometimes these sketches can get a little bit complicated when you're working with bearing. This next problem is going to be a little bit of a challenge, because what we're going to look at is to look at a situation where we want to determine before we start where we should head our airplane so that we end up going where we want to go. Let's take a look at the problem. An airplane is flying at 250 miles per hour. If the wind is 40 miles per hour from a direction of 212 degrees, what should be the bearing of the plane if the pilot wants to fly on a bearing of 315 degrees? In other words, this bearing here is going to be the bearing of our resultant. That's where we want to end up going. Okay? So we're going to have to think about this picture a little bit to get us into the right situation so that we can solve our problem. Now, let's see if we can kind of start, and I need a north direction I think I'm just going to kind of dot that one in so we don't get so many dark lines to think about here. Now, let's see if we can get some idea about what's happening. Let's work on that wind vector first, since we know exactly where that wind vector is. It's coming from a direction of 212 degrees. Okay, well, let's start from north. We know that 212 is going to be past 180, so we know we're going to come on around past 180, but not to 270. Okay, so here's that 212 degree bearing. The wind is coming from that direction. So if we're coming from that direction, we're going this way. So here's our wind vector. Did you follow that? This coming around is 212 degrees. We're coming from that, so we're really going this direction. Does that make sense? Now, let's see if we can get some kind of a measure here of some kind of an angle somewhere, okay? We know from here to here is 180 degrees because we have a straight line, right? We know the whole bearing all the way around is 212. Well, let's see, 212 degrees minus 180 degrees. What does that leave us? 32 degrees, I believe. You double check that. I kind of did that in my head quickly. 212 minus 180. Yes, it's 32 degrees. So if this is 180, this angle right here is 32 degrees. These lines are intersecting lines, so vertical angles means this angle right here is also 32 degrees. Remember all that from geometry? Okay, so we know from north over to this wind vector is 32 degrees. Okay, so we've got that much of the picture here. Now, let's see if we can do something about this resultant thing. The pilot wants to fly on a bearing of 315 degrees. Okay, so again, we start at north. 315 is going to come all the way on around. So we want our plane to be going like so. Now, since that's what we want to happen, I'm going to go ahead and call that R. From north all the way around to here is 315. Well, let's see, 360 degrees would be all the way around. 360 minus 315 degrees is what, 45 degrees? Okay, so the reason I wanted to do that, from north over to the resultant here is 45 degrees. Okay, so 45 degrees plus 32 degrees gives me what? 77 degrees. Okay? So we know that the angle from the wind and over to the resultant is 77 degrees, in case we need that. Okay? Now, let's see if we can figure out about where we need to go. If the wind is blowing this way, okay, that means as we fly, our plane is going to be moved this direction. So we know that our plane needs to start out somewhere over here, doesn't it? So that when it's blown off course by the wind, it will end up on this resultant. So we know that we need to be going over here somewhere, don't we? Let's see if we can figure out something about that vector. We know that if we take the wind vector and this initial direction of our airplane and complete a parallelogram, this will be the diagonal of that parallelogram. So this side up here is going to be parallel to this one, and it's going to have its same magnitude, isn't it? Now, I know this picture isn't going to be perfect, but let me kind of sketch in across here. We're going to have a vector that's the same as our initial airplane vector, so it's going to have a magnitude of 250. Okay? Now, our wind was a 40-mile-an-hour wind, so we know the length of that thing. I know this angle is 77 degrees. I know the side opposite it is 250. And I know this side over here is 40 degrees, don't I? So let's see if we can figure out some other angle. Like for instance, this angle maybe up here. I'm going to call it theta. Okay? Well, let's see. If I take 250, that is across from this 77 degree angle. So 250 over the sine of 77 degrees will equal my 40 over the sine of theta. Let's find that angle theta, and then we're going to talk about how we can use that. Okay, well first let's see. I've got 250 times the sine of theta equals 40 times the sine of 77 degrees. So again, we're going to divide by 250. And we will get the sine of theta here. Okay? Alright, let's see. 40 times the sine of 77 degrees divided by 250. This is about 0.1559. And we're going to do an inverse sine. And let's see, we're working with degrees here, aren't we? So let's round that off to about 9 degrees. Okay? Now, how can I use the fact that this angle up here is 9 and this angle is 77 to figure out where my airplane needs to go? Okay? Well, let's see. These lines are going to be parallel, aren't they? Parallel lines cut by transversal, alternate interior angles are congruent. So this angle right here is also theta, isn't it? In other words, the angle between where my airplane starts out and where its resultant is also going to be 9 degrees. Okay, so how is that going to help me? I know that all the way around to the resultant is 315 degrees. So if I take 315 degrees and I subtract 9 degrees, I'm going to subtract off this angle right here. So 315 minus 9, I get 306 degrees. So all the way from north around to where I want my airplane to start out going is going to be 306 degrees. So the pilot should start on a bearing of 306 degrees. The wind's going to blow from this bearing of 212 and push us over, and we're going to end up on this bearing of 315 degrees. Now we could, of course, if we were asked, find the actual speed that we would end up flying, but we were not asked that in this problem. This completes this part of the lesson on vectors. I hope that you have found these examples helpful for you. And again, I want to emphasize that if you've not had much experience with vectors, you may want to check out other videos and learn more about vectors other than what we've taught you on this tape. I would ask that you would please rewind this tape before you return it to the library. Thank you very much.